If you aim a big telescope in any direction, it'll see galaxies galore. 100 billion of them populate the visible universe, from little bits of fluff to giant elegant spirals like our own Milky Way. As the universe ages, though, the galaxies will fade away like the taillights of cars receding into the distance. The number of visible galaxies will drop from the billions to the millions to just a handful. Finally, in the far distant future, those last few beacons will fade as well, leaving each galaxy alone in the cosmic darkness. Such is the possible legacy of a force that makes the universe expand faster as it ages. Eventually, the expansion would become too fast for light to cross the void between galaxies in the visible universe. So far, we're still in the dark about this mysterious force. But scientists at the Texas Cosmology Center are joining the search for it, the search for dark energy.
Dark energy is our ignorance of what's going on in the universe right now. We think we have an idea for how the universe is supposed to expand, and so when we try to measure how fast the universe is actually expanding, it's wrong. It's actually expanding faster than what we think it should be, and that is what we call a dark energy.
In the 1920s, Edwin Hubble discovered that the universe is expanding, that all of the galaxies are moving away from each other. And the farther away they are, the faster they're moving, as a result of the Big Bang in which our universe was born. They're moving because space itself is expanding, making the universe bigger. For a long time, one of the key questions in astronomy was whether the universe would continue to expand forever, or whether there was enough matter with enough gravity to stop the expansion and even reverse it, eventually pulling everything together in a big crunch.
And for many decades, astronomers tried to detect the signs of the slowing of the expansion of the universe due to the mutual gravitational attraction of the galaxies. In 1998, it was discovered that, in fact, it's not slowing down, it's speeding up. And this is the sort of effect that can only be attributed to a dark energy, an energy in space itself.
In fact, this energy dominates everything else in the universe.
And from these various observations, we've concluded that the energy budget of the universe, as it is now, is about 4% ordinary matter. That is atoms, you, me, the sun, the moon, the stars. About 23% dark matter, which is matter but not ordinary matter, not ordinary atoms, but some kind of particles. And all the rest, about 70-some%, is dark energy.
A dark energy could be just a property of space itself, and that's the number one issue which people are considering at this point. And this is called the vacuum energy. Just the existence of space. Because space is there, there may be energy associated to that space. And the bigger space there is, the more energy there is. And that's one possibility, although the theoretical calculations are terribly off on trying to predict the magnitude of that dark energy contribution.
Another possibility is, which is quite interesting, however unlikely, is that there is something subtly wrong with Einstein's theory of general relativity, which governs the behavior of the universe on large scales, because it describes gravity, and gravity is the only force relevant in the universe on large scales. This is, however, unlikely because general relativity is a well-tested theory. In principle, it has so far served us very well in astronomy and cosmology. The other possibility is that general relativity is correct, we just are not applying it correctly to the universe.
Several teams of astronomers around the world are developing experiments to try to find the correct explanation for dark energy. Some of them will use the same technique that was used to discover dark energy in the first place, using a type of exploding star to measure the distances to other galaxies. When combined with measurements of how fast each galaxy is moving away from us, that should reveal how dark energy has changed through time, one of the keys to determining its true nature. Scientists at the University of Texas, with partners from around the world, are developing an experiment that will use a different technique. The experiment is HETDEX, the Hobby-Eberly Telescope Dark Energy Experiment. It'll use the giant Hobby-Eberly telescope at McDonald Observatory to measure how galaxies were distributed through the universe billions of years ago, a distribution affected by dark energy. And it'll test whether the energy of space itself changes over time.
Right now we're in a situation where the theorists sort of know no bounds. We've got to provide them with some boundary conditions. And in fact, what we need to do is just provide a really precise measurement of how the universe has expanded through time, against which they can test ideas. And it will probably be the case that once this measurement is in place, that 99% of the ideas, maybe all the ideas, are actually negated by it, and we find out that there's something else that we haven't thought of. But no matter what happens, any solution to dark energy is going to end up meaning fundamental change in the way we look at physics. The laws of nature will change as a result of explaining this.